So let's have a look at relations and regions of the complex plane by first starting with circles. Let's go back to the beginning and look at circles and the equations of a circle. Okay, so here's a circle, radius r. Any point on the circle has coordinates, Cartesian coordinates x and y. So center 0, 0, radius r. And so by Pythagoras we can see that the square of this coordinate plus the square of this coordinate, the y coordinate there, is equal to the square of the radius. X squared plus y squared is r squared. Specifies the particular circle we're interested in. If we now move that circle from the origin, its center is no longer at the origin. Okay, place a new center at h, x is h, y is k, still radius r. Then it's x minus h all squared plus y minus k all squared is equal to r squared. Nothing's changed there. And a specific example, here's a circle of radius 2, centered at minus 4, 3. Okay, radius 2, and we've got x minus 4 all squared plus y minus 3 all squared is 2 squared. Tidying that up, x plus 4 squared plus y minus 3 squared equals 2 squared. Nothing changes there, just basic essential circuit. Let's now take this into complex plane and look at regions in the complex plane. Okay. Okay, so let's say we need to sketch. S is the set of points complex number z such that mod z equals 2. Well, we know mod z is just a circle of radius 2. Okay, that's the modulus of the complex number is 2, so the radius is 2. It's centered at 0, it's just z by itself. And the way to see that, mod z is mod x plus iy, okay, is equal to 2. Alright, which is the square root of x squared plus y squared equals 2. Square both sides, you have x squared plus y squared is 2 squared. That's the circle of radius 2, centered at the origin. Let's have a look at a different example now. Alright, let's say we want to sketch the set S, which is the set of complex numbers z, such that mod z minus 1 minus I is equal to and less than 2, equal to or less than 2. Okay, so we could translate the circle above in the previous example in the real z direction by 1 unit, right, and also 1 unit in the imaginary direction. Okay, so 1 unit up. Okay, see how it's minus 1 minus I. Okay, z minus, in parentheses, 1 plus I if you want. Okay, you could think of that as here. Okay, as mod z minus 1 plus I, okay, equal to less than 2. Alright, so you can see that the circle has been shifted to the right by 1 because this point here has a point, it would be located at this point here, 1, 1. Okay, so our circle is going to lie at 1, 1. And we're going to have a radius of 2, but we're interested in a region now because we want everything that satisfies this inequality equal to or less than 2. Okay, so let's just have a look at what that tells us. We have mod z minus 1 minus I is mod x plus iy for the z part, minus 1 minus I. Okay, tidying all that up now is, remember this has to be equal to or less than 2, so mod x minus 1 plus y minus 1i, mod of all that, absolute modulus of that, absolute value of that, equal to or less than 2. So that's x minus 1 all squared plus y minus 1 all squared. Remember, taking the absolute value of a complex number, square root the whole of that, that's equal to less than 2. Square root both sides, square both sides, my apologies, square. 2 squared is equal to or greater than all this, or x minus 1 squared plus y minus 1 squared is equal to or less than 2 squared. So we do have a circle of radius 2. We have the points on the circle, but we also have everything within the circle. So that's all shaded in, okay? Because remember, it's a region now we're interested in because of the inequality. Okay, let's have a look at example 3. Sketch S, where S is the set of points, complex number Z, such that the real part of Z is 3. Well, you only want the real part of Z at 3, so there's no imaginary part there. That's just a straight line on the Argand diagram with equation x equals 3. Okay, it's just a straight line, x equals 3. just a vertical line straight up and down the page at 3, as it would be in Cartesian coordinates. Number 4, sketch the set S such that it's a set of complex numbers Z such that the principal argument of Z is equal to pi on 4. Okay, so what that means, it's just the points on the line. You see here, pi on 4, every point along that line there is at an angle of pi on 4. Okay, and because it's capital A, principal argument, there's only the one angle we're talking about. So capital A, principal argument, Z, that's specifying all the lines that lie on that point, lie on that line, that is pi on 4 to the positive direction of the real axis. The origin is not included. Okay, the origin can't, a point on its own can't make an angle with a line. Okay, you need 2 lines to make an angle between them, and so you must be careful. That open circle there excludes the origin itself, because the origin can't make an angle with itself, can't make an angle with the real part of the z-axis. So it's just the points on the line excluding the origin. Remember, you need a line between 2 points to make an angle with another line. You can't do that with a point. Okay, next example. Let's sketch S, which is the set of complex numbers Z, such that the principal argument of Z plus 2 minus I is less than pi on 4. Okay, so it's similar to the one above, except that we've taken our complex number Z, we've translated it 2 units to the left because it's plus 2 there, and we've translated it 1 unit up. Okay, so here we go, 2 units left, 1 unit up. It's less than pi on 4, so this time it's not the points on the line, but the points less than that. So what's less than pi on 4? Well, if I go back to example 4, the points less than pi on 4 will be all this in here. Okay, well in this case, here's our pi on 4. Okay, here's an angle pi on 4 with the real direction of the z-axis. That makes pi on 4. So all these points under here, including the negative part down here, are all less than pi on 4. All the way right round to minus pi, that's all less than pi on 4. Okay, again, we have to exclude the point, which is our translated origin. Remember, we've moved it 2 units left and 1 unit up. Okay, so 2 units left, 1 unit up. Okay, and the region that satisfies that is all where the black lines are filled in. All of that's less than pi on 4. Notice that pi on 4 itself, it's a dotted line along the line pi on 4 because we can't include the points on that because it's strictly less than. Okay, and this complex number, as you can see, has been translated 2 units left and then 1 unit up. All right, so just bear that in mind. We need to do that. Maybe, why don't I put my lines closer? And here it is. We're going 2 units left and 1 unit up. Okay, so, and excluding the origin itself, the new translated origin. All right, let's have a look at another one. Now, some more on the relations and regions. Let's sketch the set of points Z such that mod Z is greater than 2. Okay, greater than 2, but equal to or less than 3. Okay, intersection with the set of points Z, complex number Z, such that principal argument of Z is greater than pi on 3, okay, equal to or less than 2 pi on 3. Okay, now we have some points included and some not. Okay, mod Z has to be greater than 2, so really this inner circle should be broken because we can't include the points on it. It has to be greater than 2. It's equal to or less than 3, so we can include all the points that lie on the circle of radius 3, but we can't include all the points that lie on the circle of radius 2. Okay, that's what the first set's saying. So we would have the difference between those two circles if that's all we were after. But we now want to intersect that with the principal argument of Z being greater than pi on 3, so greater than 60 degrees, but equal to or less than this angle over here, 2 pi on 3. But 2 pi on 3, the points are included, so we want all that. Okay, these points here are not included, whereas these points are included. So on the top, included, on the left included, but on the bottom here, ooh, they're not included. Let me just get rid of them. I will get them once. There's my eraser. So they're not included. Okay, and likewise, the points here, pi on 3, they're not included. So that shaded region is the one we're after. Okay, that's the intersection between the two. All right, and one more. Here's another one. Let's sketch the set of points Z, such that mod Z minus 1 is equal to mod Z minus 2 plus I. Okay, you can work this on with a straight bit of algebra. Take the modulus of both sides here. So x plus iy is z minus 1. And on here, x plus iy minus 2 plus I, modulus of that. Okay, we just tied it up. Let's put the real parts together. X minus 1 here, plus iy. And then over here, put the real parts together, x minus 2, and then the imaginary parts, y plus 1i. Okay. Okay, so we have the modulus of this complex number, the modulus of this one. Let's sort it all out. Okay, so square root of this, x minus 1 squared plus y squared. Over here, square root of x minus 2 squared plus y plus 1 all squared. X minus 1 all squared plus y squared equals, square both sides, my apologies, square both sides. That's why the square root signs disappeared. X minus 2 squared plus y plus 1 squared. Okay, bit of algebra expanding all this out. X squared minus 2x plus 1 plus y squared. Over here, x squared minus 4x plus 4 plus y squared plus 2y plus 1. All right, well, plus 1 can disappear from both sides, plus y squared can disappear from both sides, plus x squared can disappear from both sides. We're left on the left here with minus 2x. On the right here, we're left with minus 4x plus 4 plus 2y. Tidying all that up, okay, we can add 2x to both sides. Bring the 2y over, minus 2y is equal to minus 2x plus 4. Divide through by minus 2. And what you've got is y equals x minus 2. That's just giving us a line. So it's all the points on the line, on a particular line, and it's the line y equals x minus 2. Well, if we plot that, okay, you can imagine Cartesian coordinates on the Cartesian plane. You know what y equals x minus 2 is. It's the line, it's a diagonal line y equals x dropped down by 2 units. So on the Argand diagram, same thing happens. We have all points lying on this line here. Okay, from minus 2i to plus 2 on the real plane, join them all up. Okay, and the way you can think of it is you can see this as the locus of all those points that are the same distance from 1, 0 as they are from 2, minus 1. 1, 0, if you have a look back here, this z minus 1, 1, 0. Okay, so 1, complex number 1, even though it's real. Over here, plus 2 minus I, okay, plus 2 minus I, plus 2 minus I, 1, 0, okay, all the points are the same distance from it. That's that.